So, we've looked at how I take a matrix and I convert it into a linear transformation. So we've seen this procedure, and it's actually set up this fantastic correspondence between kind of something very concrete and something quite abstract. So first of all, the collection of n by n matrices is basically now the same thing from a certain perspective as linear transformations from Rn to Rm. Okay, and what's a linear transformation? Well, it's just a special function. It's a special function from Rn to Rm. A bit more precisely, it's a function from Rn to Rm which preserves addition and scalar multiplication. So, I have this kind of elegant correspondence between these two ideas. And on one side, the function side, I can do various things. So we can add functions, we can scale functions, and I suppose if we're lucky we can also compose functions. So the idea behind today's lecture is the following. So the observation. We can say add, scale, and compose functions What does this correspond to? On the matrix side. So for addition and scalar multiplication, this is quite straightforward. I'm going to go through it reasonably quickly, but I'm just going to divide up what we're doing into two sides. One is going to be the matrix side, one is going to be the linear transformation side. Let's get it actually vertical. Okay, so one side it's going to be matrices, one side it's going to be linear transformations. So first of all, if I give you two matrices of exactly the same size, so I'm going to write one down as A1, A2, dot 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 to AN, and let's have another matrix B is equal to B1, B2, dot 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 to Bn. So these guys are going to be two n by n matrices. So that means all the columns are in Rm. So the columns are all in the same space. Well then, essentially we define the sum of the matrices to be, well, the term by term sum. So this is equal by definition. It's the term by term sum of all of the vectors. And really all that is just taking your terms in your matrices as a rectangular array and just summing them up term by term. So this is the term by term sum. So this is a totally reasonable definition of addition. Why is it a good definition? Well, because it corresponds to the usual definition of addition of functions. So over on the linear transformation side, I would have TA from Rn to Rm, and I would have TB from Rn to Rm. And if I have two functions with the same domain and codomain, I can sum them up. So TA plus TB, well, it's actually equal to the linear transformation coming from A plus B. So this is just sum of functions. So you're used to summing functions, I mean sine x plus cos x, for example. So really precisely, it's the following. It's TA plus tb. I need to tell you what that does to an element x. Well, we define it to be t of a of x plus tb of x. So this requires some checking. I mean, this fact here requires a little bit of thought to make sure you're absolutely definitely certain that they do the same thing to functions. That's all just kind of an exercise in chasing around vectors. So this is nice. So addition of functions, linear transformations, corresponds to this really elegant addition of matrices. Similarly, we could do scalar multiplication. So where am I? Scalar multiplication, well, I'll just jump in and define it. Lambda times a, we're going to define this to be, well, the scalar multiple of all of my column vectors. So don't worry, I know this has got abstract. I'm going to do a specific example in a second. So lambda an. So this is the term by term multiple by lambda. So we're multiplying every term by lambda, term by term. What does this correspond to? Well, lambda Ta is equal to T of lambda A. That's a really fancy way to write this down. So what does this mean? Well, we can scalar multiply functions as well. So this matrix operation corresponds to scalar multiplication of functions. So this is Ta multiplied by the constant lambda. So just think back to calculus. You have things like the constant multiple rule. You're used to multiplying functions by constants. So i.e. in this case, lambda Ta, what does it do to x? Just as the obvious thing, the only conceivable definition, it's lambda Ta of x. That's the definition, the scalar multiplication of functions. So this is nice. Scalar multiplication and addition of functions correspond to very straightforward rules on the matrix side. Let's just do a quick example. If I was to do 1, 2, 3, 4, 5, 6, this is fast becoming my favourite matrix, plus 0, 2, 4, 3, minus 1, 6, let's say again. Well, then you literally just do the term by term sum. So it would be 1 plus 0, 1, 2 plus 3, 5, 5 plus 4, 9, 2 plus 3, 5, 4 plus minus 1, yeah, it's 4 plus minus 1 is 3, 6 plus 6, 12. It's super duper simple. Similarly, scalar multiplication, 2, 2, 3, 4, 7, you just multiply each term by 2. So it's going to be 4, 6, 8, 14. Okay, so the only thing really that deserves comment here is the following remark. To sum, you have to have the same size. You can't have matrices of different size and sum them together. That's the only thing here I think that's kind of delicate. To sum, matrices must be same size. You can't add a 2 by 2 matrix to a 3 by 3 matrix. It doesn't make sense. Just like you can't add a vector in R2 to a vector in R3. It's the same essential principle. So that's addition and scalar multiplication. What about composition? Now, composition of functions itself is more complicated. Why? Because you've got to match things up. You've got to get domains and codomains to match up. And this isn't such a big issue when you're dealing with things like real-to-real functions, because kind of codomains and domains match up. But here, we've got a different domain and codomain. We've got Rn going to Rm. So we're going to have to be a little bit careful. So I'll start off just by saying the following. Composition is more complicated. What does composition correspond to? Or how can we incorporate composition of functions into this picture? So let me just start off by writing down two matrices. Let's have A, A1, A2, dot, 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 to AN, the usual business. So this is going to be an m by n matrix. So that means each of these guys are in Rm as always. Now let me choose a B, which is a little bit different looking. Let me choose a B, which is equal to, well, B1 dot 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 to BP. And I want this thing to be an N by P matrix. So I'm choosing different size for the matrix. Again, these guys now are going to be in Rn. So this is kind of confusing. We have different size matrices. Why have I done this? Well, let's convert this to linear transformations. So the TA matrix, where does it go from? Where does it go to? It goes from Rn to Rm. And what does it do? Well, it sends V to AV. That's the definition of this linear transformation. What about TB? Well, TB is a bit different. It sends a matrix from RP, is that right? Yes. To Rn. It's really easy to get this messed up. What does it do? Well, I take an X here in RP, that sends that across to BX. Now, why have I done this? This is kind of curious. Well, let me imagine trying to compose these linear transformations. Notice, by the way I've set things up, I can, I think, compose them for the following reason. If I was to do B first, that would map from RP to Rn, and then because Rn is the same as the Rn here, I could compose with TA. So I've deliberately chosen the dimensions of these matrices to get the domain of TA to match up with the codomain of TB. So let me draw a little picture. Shall I give this a crack again? Figure. Okay, so let's try this. So let's have 3 copies of this, basically. Oop. Again, do I work this out? So paste. Yep, so let's get 3 of these guys on the go. And where am I? Another one. Okay, so I don't know why that cursor's still flashing, it doesn't make any difference at all. So what have I got? So let me label some stuff. I'm going to try to make sense of this composition. First of all, where is everything? Well, I'm going to imagine this guy here is RP. I'm going to imagine this guy here is Rn, and this guy over here is Rm. Now I know they all look the same, they're not truly the same, but I can't write them down. I mean, I can do my best to demonstrate things. So here's the plan. I'm going to map from here to here using TB, and then I'm going to map from here to here using TA. So I'm going to do TB first, then TA. That's going to work because of the fact that I have the Rn in the domain of one and in the codomain of the other. So let's blitz through this. What happens? Well, let's try to keep track of everything. I get an X here. What does it map to? Well, it maps across, using my usual notation, to BX. Then what? Well, this guy, if I was to compose, it would map across to, well, this point here would be A multiplied by BX. Not multiply, we don't really know what multiply means yet, but that's what I get. I get this terminology. So first of all, what is this map? Well, this map it's some function, but it turns out, rather luckily, it's linear. So this is not totally obvious, but it's worth chasing around. The composition of these two. So remember how composition works when you write down, I'm using usual function notation, so this is the first guy, and this is the second guy. So that's why I'm writing like this. So this is composition. Okay, so this is a map now from what? From our P all the way over to our M. Is that right? Yeah. So the fact is this is linear. So the composition of two linear functions like this is actually linear again. It's a really nice exercise. You've just got to feed in an x plus y and check that it splits apart in the appropriate way. It's a good exercise. I'd advise you to do it. Anyway, so what do we need to do? Well, I think now, if I've got a linear map, it would be nice to know what the standard matrix of this. I think if I'm going to define kind of the composition of matrices, it should correspond to the composition of these linear transformations. So let's work out what the standard matrix is associated with this. So how do I work out the standard matrix? I look at what it does to my important kind of EI vectors. So let's start off. So what does this do? Well, this is equal to A times B E1. Let's just remind ourselves what E1 is. E1 is the vector 1, 0, dot, 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 0. Let's kind of wrap our heads around where is this as well. I think this is in EP. This is in, yes, this is in, this is so easy to get confused here. This is in RP. Okay, so let's just think about this. What is B E1? So what is this? Well, it's the linear combination given by the columns of B weighted according to this information here. Well, that means BE1 is just equal to the first column of B. So this is automatically equal to A B1. So again, that would be the linear combination of the A column vectors weighted by the first vector of B. Now, I could do this all the way down. So it's really important. We've got a kind of a good grasp of what the standard matrix looks like, or how to define it at least. So this is A, B, E, P. There's P of them, remember, because we're in RP. This is the last one, so this would be A, B, P. And again, here, EP is equal to the last guy, 0, 1. So what does this mean? This means the following. The standard matrix of the linear transformation TA composed with TB is equal to the matrix A, B1, A, B2, dot, 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 A, B, P. So what is this guy? Just as a quick sanity check, this is a matrix. This is an M by P matrix. Okay, so this is going to be the backbone of the definition. In fact, this is the definition, so let me just write it down. So definition. If I have two matrices above, we write down A, B. By definition, this is equal to, well, exactly what I've written here. It's this matrix. It's the standard matrix of the linear transformation given by composition of linear functions. Let's just make sure we understand everything here. So first of all, this is a M by N matrix. This is an N by P matrix. The output here is an M by P matrix. Notice the crucial thing is these have to match up for this to make sense. And this is called something, this product, if you want, the way I've written it, this is called matrix multiplication. So it's definition. I'm defining the product of two matrices in this manner. So yeah, it's worth saying this is, we can relate this back to my previous notation. So when I write AX, we can now interpret this in terms of matrix multiplication. Why? Because if I think about A as an M by N matrix, and if X is a vector, you could think about that as an N times 1 matrix. So this is just notation for a vector in Rn. And see, in this case, if I do the matrix multiplication, I'm really just doing, by definition, what I'm used to. So this can be interpreted, or can now be interpreted, as matrix multiplication. It's kind of silly because we're using the definition of AX. See, we're using this definition essentially in my definition of the matrix multiplication. So it's kind of a chicken and egg situation, basically. Anyway, this is matrix multiplication. So the key takeaway, as always, many key takeaways, the key fact. Matrix multiplication is composition of linear transformations. They're the same thing. I've deliberately designed composition of linear transformations. I've deliberately designed matrix multiplication to be the composition. Composition of functions is an elegant concept. Matrix multiplication is pretty brutal the first time you see it, especially if you see kind of this in a half-assed linear algebra course where you're kind of doing things in a very computational way. If this isn't explained to you, matrix multiplication is this mysterious thing. It's really confusing. But it's just composition of functions. So specifically what I mean is the following. If I look at the linear transformation given by the matrix multiplication, it is exactly the same thing as T8 composed with TB. That's what I mean by this. So matrix multiplication is composition of functions. So the problem with this definition, and there's no problem with this definition really, it's just it's not very easy to compute because it's pretty confusing having to write down each of these guys. There is kind of a quick way to do it, which I'll explain now, which is, it's the same thing, it's just kind of a fast way to work out the individual terms. So let's do it. Here's a cool kind of rule, I'll call it the row column rule. To compute AB. So how do I work out the entries of AB without having to go through this gruesome procedure? Well, it is going to be pretty gruesome, but it's not going to be so bad. So if I have the product AB and I want to know the ijth entry, so this is my notation for the ijth entry. So remember what the notation is? That means you're in the ith row and the jth column. It turns out this is equal to the following thing. It's equal to, so I'm going to write it down to begin with. It's not going to be terribly illuminating, but I'll draw a picture to help. AI1 B1J plus AI2 B2J, and it follows that pattern until it's AIN BNJ. Now that is really useless the first time you see it. Let me actually draw what this means. So if I take my two matrices, I'll draw them side by side. That's going to be my A, and this is going to be my B. I don't know, something like this. Now remember to get everything to match up before we do anything. So this is going to be my A here, this is going to be my B here. For this to match up, to be able to do a matrix multiplication at all, you need to get the dimensions to be appropriate. So that and that, so the width of the first has to be the same as the height of the second. That's the first thing. N by N, N by P. Is that right? Something like that. I hope so. So let's write down the ith row and the jth column. So if I write down the ith row, it would be AI1, AI2, dot, 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 to AIN. So this here is the ith row. And let's do the jth column. So the jth column is B1J 2j, dot, 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 God, it's so confusing, bnj. So this is the jth column. So what are we doing? Well, we're pairing these up, multiplying and adding. It's not so bad. Let me just kind of use different colours to indicate. So that and that pair up, right? They correspond to this. You take the product there. And you kind of work your way along. So that now and that pair up, and they correspond to this. And you just go all the way down like that. So you work your way along the row and the column. It takes a bit of practice to get used to doing it, but it's kind of natural by the end. So this and this kind of pair up, and that's what gives you this. So that's the basic procedure. So you've got to do that with every position. So it's pretty gruesome, especially if you're told this without realising it's just composition of functions. It's the most weird rule ever. But all we've got to do is just do an example. Hopefully it'll make sense. So let's do the following. So imagine I was to work out the matrix multiple of 1, 2, 3. I'll mix it up a bit here. 4, 5, 6. And then I'll do 1, minus 1, 0, 2, 1, 1. Does this work out? Can I multiply these? Well, this is a 2 by 3 matrix. This is a 3 by 2 matrix. So yeah, the 3 and the 3 match, so I can take the product. What do I expect to get out? I expect out to get a 2 by 2 matrix. So let's go through it. I'll write this out longhand. So the first one, I have to go along the first row in the first column. So I would have 1 times 1 plus 2 times 0 plus 3 times 1. That's the first piece. Then I'll move across to the next, this guy. So then it's 1 times minus 1. Is it plus 2 times 2 plus, oh God, 3 times 1 again. Then I'm going to move back to this position, and I'm going to move the row down to there. God. 4 times 1 plus 5 times 0 plus 6 times 1. I hope that's correct. And then finally I'm going to move this guy across to here. Same deal. 4 times minus 1. Oh man. Plus 5 times 2 plus 6 times 1. And of course now at this point you can simplify. And hopefully this is equal to 4. God, then what is it? 4 times plus 3, 7, minus 1, 6. 4 plus 6, 10. What's the last one? 6 plus 10, 16, minus 4, 12. That's the matrix multiplication of this. And it's just the composition of the linear transformations associated to it. And notice, of course, well, notice this is a 2 by 2 matrix, as you would expect. Something terribly wrong would have happened if that wasn't the case. Okay, so now let me just go through a few properties of these algebraic operations and matrices. You've got to be careful of them because they kind of behave in ways that you're familiar with, but there are some things about them that go a bit haywire. So properties. Of matrix operations. Okay, so the first thing is multiplication is associative. So what that means is, assuming I can multiply, so you've got to get everything to match up, well, it doesn't matter what order you do it in. That needs checking. That's quite hard to show. Really, it's because composition of functions does this too. Similarly, there's an interaction, assuming things match up in terms of size, there's an interaction between addition and multiplication, kind of like the distributive rule for multiplication and addition of ordinary numbers, plus AC. Well, we also have the following. You can do it on the other side as well. That splits apart too, so it's AC plus BC. It's nice. Similarly, you have, if I do kind of lambda, if I scale the product, that's equal to what? Lambda A, B, which is equal to, you guessed it, you can just move the constant around freely because it's a constant. 5 multiplied by the identity matrix is nice, it really doesn't do anything. You've got to be careful because you've got to be on the right dimension on either side. But if it's an m by n matrix, multiplying on the left by the identity matrix, the mth identity matrix m by m, so you can do it, that just gives the same matrix back again. Multiplied by an on the other side, same thing. Okay, so these are lots of things that it has in common with ordinary arithmetic. There's a big warning though. Common error. In general, AB is not going to be equal to BA. So that's a pretty huge difference. Addition, it's fine. A plus B is equal to B plus A, but matrix multiplication is weird. And I'll tell you why this is true. I mean, if you take two functions and compose them, you already know this. It matters hugely which you do first. Composing sine and cos, sine composed with cos is not the same thing as cos composed with sine. So same deal here. Matrix multiplication is composition of functions, so unsurprisingly it's not going to have this nice property that AB is equal to BA. So this means it's not commutative in fancy terminology. Not that that matters. Other things to be careful of. Also, this is pretty horrific as well. So if the product of two things is the zero matrix, so that's the matrix which is zero everywhere, this does not imply that A is equal to 0 or B is equal to 0. This is crazy, right? So you can have two things multiplied together to give 0, but neither of them is 0. And again, it's because it's not really multiplication. This is kind of a different concept. Really, it's composition of functions. Just as a quick example, e.g., 0, 1, 0, 0, 0, 1, 0, 0. The product of that with itself is the 0. So this is something where you have something which looks very similar to the usual operation of multiplication, but in some ways it's totally different. A consequence of this is the following. AC is equal to BC. You might think you can cancel off the C, but this does not imply that A is equal to B in general. So that's another thing which is different. Even when C is non-zero. Right? If C is non-zero, you think you could cancel it off because you're used to doing it with numbers. Okay, because you can divide through by something non-zero. But this fails. This fails in general. It's disastrous. Okay, so you've got to understand the matrix operations are good in loads of ways, but are bad in others. And this is the kind of thing you would study in more detail if you go on to do kind of abstract algebra in upper division mathematics. Okay, so one final thing I want to do is introduce a new operation, which is kind of quite different than the others. It doesn't correspond to something really obvious at all in terms of even the linear transformation side of things. But I'm just going to give us the definition. It's going to turn up a few times, or quite a lot later in the course. So there's a funny thing I can do to a matrix. So if I give you an m by n matrix, I'm going to define A capital T. So this is going to be called A transpose. A transpose. And the definition is the following. Well, I just need to tell you, the definition is I need to tell you what the ijth entries are. Well, I define the ijth entry of the transpose to be the jith entry of your matrix. So you kind of flip the indices. As a quick example, e.g., it's a strange operation, this, because it doesn't have anything obvious to do with linear transformations. You can express it in terms of linear transformations, but it's more sophisticated. If I have that as A transpose, well, this is a 2 by 3, so this turns into a 3 by 2. So this is equal to, you kind of flip everything. It's 1, 2, 3, 4, 5, 6. So doing a transpose switches your n and your m essentially. So this is 2 by 3, and this is 3 by 2. So again, this is kind of a thing which is natural to do on the matrix. It's quite easy to do this, but in terms of the linear transformation, it's not so obvious. Like I said, it will turn up and be quite important later on in the course for certain specific types of matrices, but let me just give you a few facts before we finish. Most of these are pretty obvious. A transpose is A again. Not much of a surprise there. It behaves very nicely when it comes to addition. If I have two matrices of the same size, I sum them, take the transpose, that is the sum of the transposes. It behaves very nicely with scalar multiplication. You can just take the constant out the front. The only one which is a bit more interesting is multiplication. And this is really not obvious. This requires a bit of thought. AB transpose, it's not A transpose times B transpose. You know it can't be, because if you try to write that down, you'd realize the numbers don't match up. This turns out to be equal to B transpose times A transpose.